So today we're going to learn the last of our, major derivative rules. And there's a list of 4 functions, and we're going to be able to take the derivative of 3 of them, but not one of them. And so this first one, we can use our fresh new product rule. We can find the derivative of that pretty easily. And you could say the same thing for the second one. We could use our quotient rule. Okay, this one, yeah, we could use product. That's an interesting thought. We could use product. Anybody have another way that we could maybe take it without it being too difficult? No, you don't know how to do that yet. Yeah, you could expand the thing. You could actually square x squared plus 3. You'd get something like x to the 4th plus 6x squared plus 9. Either way, we could do that. But sine of x squared, that's something, yeah, we don't have the tools for that yet. Some of you, it appears like you do from maybe a physics course, or maybe you took Calculus AB last year. It puts you at a distinct advantage here, especially when taking the derivative of sine of x squared compared to everybody else who doesn't know that yet. So yeah, we're going to need a new rule for this. So today we're going to, develop a rule for taking derivatives of positive functions, right? Because the sine of x squared is a function where we take a number, we square it, and then we take the sine of it. So when it comes to f of g of x, we're going to take the derivative by starting with the outside function and leaving the inside the same. Then, to account for the fact that there is an inside function, we're going to take the derivative of that and multiply it on the outside. So, there's kind of another way that I could write this too, is that dy dx is equal to dy du multiplied by du dx. If u is some sort of like intermediate step in there. I know y'all will probably like it, right? It looks like the du's cancel off, and I would say that's really not how that works, but it's okay. Because functionally, it does work. So I'm not going to include the proof today. That's another one of those things that I'll have to come back. I'll loop back around and show you. This one is to be a little more interesting algebraically. Still at y'all's level. Y'all could follow it. And if you're really that interested, I'd say just look it up on the internet because you can follow it. It's purely algebraic. So, for example, let's just go ahead and take the derivative of sine of x squared. So in terms of this, I'm writing green, so I'm going to do it in terms of this y, u, and x. Really what you could say is that y equals the sine of u, where u equals x squared. And I won't be doing it like this really after this example, but this is one way you can think this way. Over time, using the chain rule, it'll just become second nature, not a big deal. So y equals sine of u, u equals x squared. So dy du is just going to be the derivative of this thing with respect to u, and it's going to be cosine of u. Du dx is equal to 2x. Therefore, we know that dy dx is here, dy du multiplied by du dx. And so I'm going to say that that is cosine of u times du dx. And u was x squared. Okay, so what I can do is I can say, I'm going to kind of reconcile this with what I've written up here. I'm going to say, well, this is equal to take the derivative of the outside, which is sine. The derivative of sine is cosine. We leave the inside the same. And then we multiply by the derivative of the inside. The derivative of x squared is 2x. And you can rewrite that as 2x cosine of x squared if you like. That's fine. So that's how we do the chain rule. So I'm going to move pretty quickly through the examples because there's some other things I want to show you there too. So I'm going to start with f of x is 2x squared plus 3, then squared. And yeah, we could probably, expand this out and take using the power rule. But what if this was 2x squared plus 3 not squared, but to the 5th power, right? You remember from Algebra 2. If you remember all the way back to Algebra 2, when we expanded binomials to the 5th power, how unpleasant that was. Yeah, we used Pascal's triangle, even though, actually that was probably the way to go. That was met with endless complaining in Algebra 2. I remember it vividly. So what we're going to do is we're going to, ramp it up to the 5th power, and I'm going to take the derivative. Okay, so really kind of key is to recognize what's the outside and the inside of these functions. Okay, well the outside is that we're taking something to the 5th power. So I know how to take the derivative of, say, u to the 5th. It's going to be 5u to the 4th. So 5 times, leave the inside the same, knock the power down by 1. Then, to account for the fact that this has got its own derivative, I'm going to multiply by the derivative of 2x squared plus 3, which is 4x to the 1 plus 0. And so this, if you felt like you couldn't live with it being written like this, you could rewrite it as 20x times 2x squared plus 3 to the 4th. And, of course, you could expand 2x squared plus 3 to the 4th, but where would that leave you? Would that leave you with a derivative that's any easier to calculate for a given value of x? I don't think so. I think it would just be a waste of time. So, next, here we've got a square root thing. We've got 5x to the 4th plus 3 square rooted. Okay, well, we know from a couple times ago that it's easiest to rewrite this as 5x to the 4th plus 3 to the 1/2 power. So, y'all give this one a try, see how you're doing. So you see, I've written it up there, and this would certainly be a safe place to stop if that's where you wanted to stop, but if you wanted to simplify and make it look familiar, or the way you liked better, we could write it like that too. They're the same. Okay. So, next question is, what's the difference between sine squared x, sine of x squared, and sine of x squared? Two of these are the same, and one is different. Right, which two are the same? Yeah, the first one and the last one are the same. Right? And probably, if we're using parentheses, especially if we were like super judicious with our use of parentheses and we did it like that, that would probably be the best way, the clearest way to write this concept. Taking the sine of an angle and then squaring it. That would probably be the best. But we use this sine squared x, we have for quite a long time. So, sine squared x equals sine of x squared. So it's like we're taking an angle, we're taking the sine of that angle, and then we're squaring. Sine of x squared is we're taking the angle, we're squaring it, and then we're taking the sine. So we already took the derivative of sine of x squared right here. That was the first one we did, so I'm not. But I will do sine squared x. In fact, I might take two derivatives. Let's see how that treats us. So f prime of x is going to equal, well, I think it might actually be easier if we rewrote this as sine of x squared. So it was more clear what the outside and the inside was in terms of like our chain. Okay, we're going to take the 2 and we're going to bring it around the front. That's the power rule. We're going to leave the inside the same. And we're going to knock down the power by 1. Then we're going to multiply by the derivative of the inside, and the derivative of sine of x is cosine of x. And that equals 2 sine of x times cosine of x. Now, if you just like really loved your trig identities, or you paid super close attention in your trig class or whatever, you might remember that this is also equal to sine of 2x. Okay, if you don't, it's not going to lessen the richness of your experience in this course, but it will mean you'll have to take the product rule to find the second derivative rather than the chain rule. So what I'm going to do, I'm going to take the second derivative, and I'm going to use the product rule. I didn't know how to do that last time, so might as well use it again today. I'll take the derivative of 2 sine x, and that will be 2 cosine x, while leaving cosine x the same. And then I'll add in, leaving 2 sine x the same. The derivative of cosine x is negative sine x. Okay, so this is 2 cosine squared x minus 2 sine squared x. Okay, so that's the second derivative. Over here, I can take the second derivative. Okay, so that's f prime. If I wanted to take the second derivative, I could use the chain rule on the way I've written it over here in pink. So f double prime is going to be, okay, start with the outside. The derivative of sine is cosine. Leave the inside the same. And then multiply by the derivative of the inside. The derivative of 2x is 2. So this is 2 times cosine of 2x. Okay, what's the deal? I mean, I see I've got cosine squared minus sine squared here, and then I've got cosine of 2x. Is this the same? If I made an error somewhere, like, well, what is the deal? It is the same. That's actually another trig identity. It's the cosine of 2x is cosine squared minus sine squared. Yeah, if you take out the 2, cosine squared x minus sine squared x is cosine 2x. We know what cosine squared x plus sine squared x is. That's 1. Everyone knows that. But this one, maybe a little more obscure. Cosine squared x, really it works the same way, so I don't think I'm sure that'll be one of the homework assignments, or one of the homework problems tonight is take the derivative of cosine squared x. So I'll leave that one to y'all. Let's see what else we got. Multiple layers of chain rule. This is what we need. Okay, this is the tricky stuff. Right? It's the thing that you're going to ask me about on Tuesday. When you come in before the quiz, you're going to ask me to do one from the textbook. It's going to be like 5 layers. It's going to be really impossible. But it won't be that bad. So dy dx. Oh, wait a second. Really, my advice is anytime you see this, like, sine squared, sine cubed, something like that, rewrite it. Okay? So we're going to take the sine of 4x squared, and then we're going to cube that. So dy dx is going to equal, start with the outside, it's powerful, 3 times, leave the thing on the inside the same. Reduce the power by 1. Now multiply by the derivative of the inside. Now the derivative of the inside is going to be, the derivative of sine of 4x squared. Well, that has its own kind of chain rule. We're going to take the derivative of the outside, which is the derivative of sine is cosine. we're going to leave the inside the same. And there's it, and another inside. There's the derivative of this 4x squared. The derivative of 4x squared is going to be 8x. And, we could maybe work this around. We could write it differently. Or we could not. And I'm going to actually stop here. That's fine. Yes. This is certainly the type of problem that you could expect to see on a quiz. Or on the multiple choice section of an AP exam. Very typical type of problem. I think I'm going to skip the one. There's one to the right of this. I'm going to skip it in order to get maybe some e to the x and log x stuff, maybe. Oh, multiple rules at once. Why not? Sounds great. I bet this looks like it's going to have product and chain. All right. So when I'm going to go to take the derivative, let's say f prime of x equals, I'm going to start with the derivative of x squared, because that's easy. 2x times, leave this the same. And I'm going to add in, leave x squared the same, and take the derivative of 2x to the third minus 3 to the fourth. Okay, well, I'm going to start with the power rule. That's that fourth power. I'm going to bring that down. Leave 2x to the third minus 3 the same. Reduce the power by 1. Then multiply by the derivative of the inside. The derivative of the inside is going to be 6x squared. And that's good. It's product. We're taking the derivative of the factor on the right, the 2x to the third minus 3 to the fourth power. Remember the chain rule. That's good enough. Oh, this is a kind of some other random question that I've found. This quotient rule one, this would be a good thing for us to do, but just in the interest of time, I might come back to it. So let f of x be a differentiable function. The line tangent to the graph of f at the point 36 passes through the point 528. Find the value of f of 3 plus f prime of 3. Okay. So all the information we need to solve this is right there for us. Take it one piece at a time. F of 3, that's the easy one. What is f of 3? Can we see what f of 3 is? It's 6, yeah, because the point 36 is on the graph. So f of 3 equals 6. 6 plus some other. Okay, f prime of 3. And we know we're going to have to use this other point. They gave us 528. That's some weird numbers. What could we potentially be doing? Okay, so yeah, the line tangent, they gave us 2 points on the tangent line. And with 2 points, we can calculate the slope. We're right in the thick of that in college algebra. Slope, intercepts, parallel perpendicular lines. So I might say, I could use the slope formula using this point and that. And remember, it's rise over run. You'd be amazed how many things in this calculus course are going to come down to rise over run. Okay, so it's going to be y2 minus y1 over x2 minus x1. Okay, so that's going to be 22 over 2 is 11. Okay, so it's 6 plus 11, so that value is 17. And this is really the type of, I know that this is an AP multiple choice question. Like maybe the numbers are slightly different, but I've seen this question before. So I think, and I really liked that question. So that's probably why I included it. This is different question. Through this exponential function. More theorems that we're not going to get the proof of. This one we're actually, I don't think, ready for the proof of it yet, but I'll loop back to it. Okay, so the derivative of e to the u is, we said last time, it's e to the u. But when I'm taking the derivative of e to the u with respect to x, u could potentially have its own derivative. So that's where we'll say it's e to the u multiplied by the derivative of u with respect to x. And if you look in the back of your textbook, they've got a table of derivative rules. They'll have a table of antiderivative rules too, but we're not going to. But you'll see they write it like this all the time. They'll say that the derivative with respect to x of sine u is cosine of u du dx. Because they're, you might run into something that's not just the derivative of sine x. If you go back and look at all the derivative problems we've done up to this point, it's always been sine of x, cosine of x. Never sine of 2x, never sine of x squared. Okay, we've been doing most of the simple ones. And now we're going to, this will really open up the library of functions that we can take the derivative of. And then we can take the derivative of natural log, saying that's 1 over u multiplied by dx. Whatever the derivative of the inside of this. With these facts, I'm going to give you a couple of corollaries. Post 63 might call this a correlate. Is that true? Is that what you would call this? 63. One time I had an algebra professor that was really busy. I know that's a very far away from. Okay, so the corollary would be that the derivative with respect to x of some number to the, I'll actually just say maybe 2 to the x. Is going to be natural log of 2 multiplied by 2 to the x. And I'm going to show you why this works. Remember that 2 to the x is equal to e to the natural log of 2 multiplied by x. Okay, so now I'm going to use the chain rule. The derivative of e to a thing is just e to that thing. But remember, we've got kind of an inside. We've got natural log of 2 multiplied by x. And natural log of 2, that might be a scary looking number to you, but at the end of the day, it is just a number. So I'll say that the derivative of natural log of 2 times x is just going to be log of 2. So multiply that by log of 2. And then, but then I could kind of put the pieces back together and say e to the log of 2 is 2. So that's 2 to the x multiplied by the natural log. This is a very rare thing. It's rare enough that I actually recommend that you solve it like that. I think I showed you how to take the derivative of log that's not base e last time, and so I'm going to skip over that in the interest of making a problem. I didn't show you that. I'll show you all that in the You do something very similar. Use the change of base formula. It won't be. Okay, so I'm going to switch over to some multiple choice. Oh yeah, here it was. So we found out that that was the right answer. Okay, number 6 from your multiple choice packet. Cosine squared of 3x. Okay, well, I'm going to rewrite it, right, because I see that cosine squared. I think that's generally best that we do that. Cosine of 3x plus 2 squared. And so y prime, I'm going to bring that down around the front. Reduce the power by 1. Take the derivative of cosine of 3x, which is going to be negative sine of 3x. And then there's another layer, so we're going to have to multiply by 3. And now it's like, oh, I got to reconcile this with the answer choices. So I'm seeing one thing that can kind of help sometimes is I know I've got a 2, a 3, and a negative 1. So there needs to be a negative 6. Okay, so I can basically choose that based on the response. All right. The slope of the line tangent to the graph of y equals log of x squared. What a perfect question to end on. I'm going to take dy dx. That's going to be 1 over x squared. Multiplied by the derivative of x squared is 2x. Okay, so dy dx at the point where x equals e to the 2 is going to be 2e to the 2 over e to the 4. So I believe that'll be 2 over e to the 2. So that's choice B.